Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And within that playlist, I create little mini-series that correspond to different design of experiments. This mini-series, we're looking at Randomized Complete Block ANOVA, and this is part 3 of a 6-part series. And in here, we're going to look at the sum of squares and an F-test for this setting. Now, a lot of what we do here mirrors almost identically the mini-series on repeated measures, one-way fixed effects ANOVA. And specifically, I'm going to point you to part 4, which is the sum of squares derivations for this design. I'm going to call it BV1, which stands for Background Video 1 that I want you to watch, and BV2, Background Video 2, which is part 5. And that's the distributional properties of the sum of squares that we derive in part 4 for the repeated measures one-way fixed effects ANOVA. But here, again, reminding you, we're in the randomized complete blocks ANOVA. So our model is this: y equals x beta plus air, and it can be broken down into these 3 column spaces, the mu, x tau, and x beta, where epsilon is normally distributed, mean zero, and variance covariance matrix sigma squared I. And part 1 in this little mini series you can watch for much more detail. Now, the sums of squares for this complete block design, what we do is we take the total sum of squares and we break it or partition it into the sum of squares due to treatments, sum of squares due to the blocks, and then sum of squares error or residual. And in matrix form, it's this. This is sum of squares total, sum of squares treatment, sum of squares block, and then this is the sum of squares error. Now, you can always create the sum of squared error by I minus M. In any design we do. That's it. But when we're in special cases, special design of experiments, it sometimes takes special formats, or it assumes a special format. And M in this design is M tau plus M beta minus J. So, and I write it like that because then it kind of helps me think about breaking this into scalar form a little easier. And scalar form is this. This is sum of squares total, sum of squares treatment, sum of squares blocks, and this is the sum of squared error. And the reason I see that is when you take the y into each of those, you get the grand mean vector, the block mean vector, and the treatment mean vector. And see part 2 for a little more detail of that. But in BV1, we go into great detail in breaking these sums of squares into their respective parts. So I'm going to point you to there for the specific derivations. Now, the degrees of freedom are associated with the matrix in quadratic form. So the total degrees of freedom is the rank of this matrix. Now look at this. So the total degrees of freedom. Oh, let me come down a little bit. So this is total. This is I minus J. That's why we're looking at the rank for sum of squares total. Now, since I minus J is an idempotent matrix, the rank is the trace, and then we've shown in the previous video the trace of this is AB minus 1. The treatment degrees of freedom deals with the rank of this matrix in quadratic form. And again, it's an idempotent matrix. It's a perpendicular projection matrix specifically, and every perpendicular projection matrix is idempotent. So it's the trace, it's A minus 1. The rank of degrees of freedom for blocks is the trace, and it's B minus 1. The error degrees of freedom is the rank of I minus M, and then M takes a special form in the complete blocks design. M tau, M beta, and J. So the trace of this just ends up being AB, A minus B plus 1, and it can be written in this product form, A minus 1 times B minus 1. Now the expectations of the sums of squares, I'm going to point you to BV1 where we partition the sums of squares and we calculate the expected values. And here the expected value of sum squared error is a minus 1, b minus 1 times sigma squared. And actually looking at that, we can, if we divide both sides by this constant, then we create an unbiased estimate for this sigma squared, the error variance. And then, of course, when you divide it by its degrees of freedom, it's called the mean squared error. Now, expected value of sum squares treatment is this, a minus 1 sigma squared plus b times this. And look at this, that we're interested in the effects of treatment. And so if there's no treatment effect, all the effects are the same essentially, or zero, then I wouldn't say zero. They're all the same. And that means they equal their mean, right? So then this is zero. And if under the null hypothesis, this is zero, and that's kind of how we get a central chi-squared. But under the alternative, this is not zero, and it shoves the test statistic way into the right tail. Expected value for sum of squares block is this. Now, the distribution of the sum of squares is this, and again, I'm going to point you to BV2 where we derive these in great detail. We actually make use of theorems in a video that I called Distribution of Quadratic Forms. I have like 3 or 4 parts to that video, 3 or 4 videos, each one increasing in complexity. So the distribution of sum squared error divided by sigma squared is a central chi-squared with a minus 1, b minus 1 degrees of freedom. Sum squares treatment divided by sigma squared is a non-central chi-squared with degrees of freedom a minus 1 and non-centrality parameter b times this sum. And this is what I was saying under the null hypothesis. This is zero and it becomes a central chi-squared. Sum squares for block divided by sigma squared is a non-central chi-squared with b minus 1 degrees of freedom and then a times this sum. And again, like we're not interested in the block effect much, so we don't really do this test. But if we did, the numerator would be there's no block effect, which means all the BJs would equal their mean, and then this would be zero and be a central chi-squared. But the test statistic that we use involves the sum squares treatment and the sum squared error, and it requires that they be independent. And I have a video on the independence of quadratic forms, and it's essentially if you take the matrix in the middle of these quadratic forms and multiply them, assuming the y's are normally distributed, and we do. If this is zero, then these quadratic forms are independent. And if you multiply this out, remember m is m tau plus m beta minus j, so that you do the minus m, and then I minus tau is I minus m tau is m tau times m tau, it's idempotent, so you get it back, and then actually those two cancel each other. M beta m tau is j and m tau is j, and then when you take j times each of these, you get j back. And if you do that math, it ends up being zero. Now the hypothesis that we're of interest in, is there a treatment effect? Or is there not? So the null hypothesis that there's no treatment effect. So the effect of treatment is the same for each level of the treatment. So that means it equals its mean. And so this means no treatment effect. This is for all I. Versus there is a treatment effect, meaning one of the treatment effects is not equal to the mean. It's different from the others. And this is for some I. The test statistic is the ratio of these two chi-squareds divided by its degrees of freedom. Now, remember, the numerator is a non-central chi-square distribution. So that makes this a non-central F distribution. And so this is the numerator degrees of freedom, the denominator degrees of freedom, and this is a non-centrality parameter which we obtained from this. Now, under the null hypothesis, this is zero and it becomes a central chi-square distribution. A note, again, the test for block effects is generally not of interest, and we usually don't conduct those tests. The fitted value for this model is always my. Remember, this is a perpendicular projection matrix on the column space of x. So if you take a y vector, and I always think of it as like a dangling vector, so it's out there in space somewhere, and you pre-multiply it by this perpendicular projection matrix, it actually shoves it down into the column space of x. So we're using the linear combination of x's to come up with our best guess, and that's what this is doing. But when you pre-multiply by m, it puts a hat on y, and that's actually kind of why they call this the hat matrix, because you pre-multiply y by it and it puts a hat on y. Now m, of course, in this model is this, and then when you multiply the y into each of those, you get the treatment mean, the block mean vector, and the grand mean vector. And so this is it. This is the fitted value. And when we do part 6, where we use an R illustration, we'll illustrate this. And to me, it's just so fascinating how it works. Now in scalar form, it's yij hat is equal to the ith mean plus the jth block mean minus the grand mean. Now the residuals is what's kind of left over when you take the y, our original response, minus our fitted value. You hope that it matches exactly, and that'd be the best case, but it rarely does. So there's always something left over. And that's called the residual. We call it E. Now y minus y hat, if we replace what y hat is, my, and then we right factor out of y, and these are the residuals. Now in scalar form, Eij is equal to, of course, the data point, Yij, and then it's minus the ith mean, the jth minus the jth mean, and plus the grand mean. And that's the fitted value. And we will illustrate this in R. It's kind of cool. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.